had reached the last time. We knew how to construct, we now know how to construct deterministic Bisha automata for these two easy fragments of LTL. Oh, yeah.
So last time you said something about why did you choose F and then Q and next operator?
Ah, right. Okay. So I have to give you an answer about that. Good. So
Repeat the question.
The question is, well, I actually asked you the last time, why do you choose next and until as basic operators, right? The obvious choice would be to choose something like next and eventually, right? And maybe you would generate them globally and so on. Well, how many of you know about the notion of expressive completeness of a logic? Okay, quite a few. So the idea is always when you give semantics to a logic, you have to actually give it in another logic, right? Because the semantics you have to describe formally, right? If you wanted the semantics to be described formally, actually all you are doing is embedding a logic into another one. So the typical, I mean, the logic you are doing this with, in which you are doing this with LTL is the first order theory of the linear order, okay? And then what you would like to have is expressive completeness. What you would like to have is that your new logic, or I mean, if it's possible, right, that your new logic is as expressive as the logic that you are using to describe the semantics of the old logic. Well, if you only take F and G, for example, as linear operators and as temporal operators together with next, then that's not expressively complete. And therefore, one would like to have something else, right? I mean, even though in many applications it's already enough, one would like to have something else, and you would like to see if you can achieve expressive completeness. And when you add the until, you have expressive completeness. It's not the only way to achieve expressive completeness, but it's one relatively simple way, because the until operator still has a very intuitive semantics, right? And, well, that's the reason why you have until.
The way you framed it, I would have framed it differently.
Okay.
The way you framed it, you set yourself up. Because if you have the temporal logic with just, let's say, X and F,
Yes.
it can be defined first order logic with two variables.
Yes.
And it is as expressive as first order logic with two variables.
Yeah, but who wants first order logic with two variables, right?
But now it's not science.
Okay, now it's not science. Anyway, that's my answer to the question. Anyway, the important thing is that it is interesting to know that LTL is expressively complete, which is actually a result that goes back to the 60s, was proved by Kemp. It's actually a very nice theorem. Anyway, so, right. So, and we saw that these are going to have at most 2 to the n states because of a simple argument about Boolean functions with n variables. So the next question, and we said, yeah, this came, right? And the next question is, okay, well, if 2 to the n is pretty much, so if we allow NBAs, if we allow non-determinism, can we get maybe a smaller automata? We know that non-deterministic automata can be more compact than deterministic ones, right? And yeah, there is a very simple way to do that, still using the after formula, right? And the idea is that you always keep this, imagine that you always put this in disjunctive normal form, okay? And you look at it as a conjunction of clauses, okay? But this is the disjunctive normal form, not a, sorry, a disjunction of clauses. It is the disjunctive normal form, not the conjunctive normal form. Well, then let's this be the set of clauses that you can you have in the formula, right? And then you can define actually the set of clauses that you can reach, that you can generate when you are unfolding the formula, right? When you are constructing this after formula. And now, well, it is easy to see that this set of clauses is going to contain at most 2 to the n clauses, right? Because your formula has length n, it can have at most n temporal formulas. A clause is going to be a conjunction of temporal formulas, so you have at most 2 to the n, right? And how can you construct the NBAs? Well, the NBAs, you know, imagine that this is the DFA we had for this formula. Well, now we are going to put this thing in disjunctive normal form, or all these things in this disjunctive normal form, right? And then what you do is that you have to satisfy here either GB or XXA, so you can guess which one you are going to satisfy, right? So in the NBA, what you do is your states are the clauses, okay, and you just keep guessing which is the clause that you are going to satisfy, that is going to hold, right? Whenever you have a disjunction, you can choose. And therefore, your NBA will be constructed in exactly the same way with the states and clauses, and then always going from a clause to, with a letter, to all the possible clauses that you could have next. Everybody happy with that? Yeah? Good. So, okay, so this will be the NBAs for these two fragments, right? Essentially the same, but the states, instead of being the formulas you can reach, it's just the clauses you can reach in disjunctive normal form. Good. So let's go one step further, right? And now let's consider, just humor me and consider this fragment, yeah? Infinitely often, and then something in this fragment, in this co-safety fragment, you remember these are the operators F, U, and M, right? So how can we construct a DBA for this? Well, you know, if phi is a formula in this fragment, then f phi is also a formula in the fragment, because, you know, we are allowed to use the f operator. So we are going to have a DBA for this, right? It's going to look like this, an initial state, and true is the only final state. And when you reach true, you are going to stay there, and you know that you have satisfied the formula. So now what do you do for GF? Well, you just add an arc, essentially an epsilon transition, if you want, which you can then eliminate, right? And this will be your DBA for the fragment. Everybody happy? Good. So what about constructing a DBA for, let's consider this dual.
DBA on NBA.
Okay, let's construct an MBA first, right? An MBA for the fragment FG and then GWR, right? Well, if you have that, actually, there is a typo here, right? If phi is a GWR formula, then G phi is also a GWR formula, and then you are going to have an MBA for it, right? Or even a DBA for it. And the DBA is going to have the only non-final state, non-accepting state is going to be the false, right? So if you want an NBA for it, you can always do it easily, and there is another typo here, sorry. This should be FG, okay? You can do it just like this by putting an FG there, right? This is going to be the formula FG, and then you stay there until you guess the right moment at which G phi is going to hold, right? And then probably the thing you know, or I mean actually the thing that Bernd told you yesterday, is that the problem is that we cannot have a DBA for it, right? And why not? Because we cannot have a DBA even for this simple formula for FGA. And actually Bernd did something very elegant yesterday, which is that when you don't want to explain something in detail, you always say, and Javier is going to tell you everything about it, right? Well, anyway, we all know this is the old trick in a school. Anyway, so let's go also quickly through the argument. So how do you prove that FGA is not recognized by any DBA? So, well, just by contradiction. So assume that some DBA recognizes the language of FGA, right? Which assume that your atomic propositions is just A, right? So in fact, then it is actually this language. So you can have either A holds or A does not hold, right? And then, well, let's just for simplicity, let's call alpha the case in which A holds and beta the case in which A does not hold, right? And then your DBA, by assumption, accepts alpha omega, okay, because this is the language which contains only finitely many betas. So if you look at the DBA as a DFA, right, this is the same automaton, then the DFA is going to accept alpha n0 for some n0, because it has to reach some accepting state, right? So the DBA then, by assumption, has to accept alpha n0 beta alpha omega, because this only has one occurrence of beta, right? And then the DFA has to accept alpha n0 beta alpha n1 for some n1. And this goes on, right? Your DFA has to accept alpha n0 beta alpha n1, alpha n0 beta alpha n1 beta alpha n2, and so on, right? So now what happens when you consider then this sequence, right? Remember that your automaton is deterministic by assumption. So this means there is exactly one run on this word, right? I mean, or make this word as long as you want. It's always going to be the same run, and then if you make it longer, you extend that run a little bit more, right? So then you look just at the states that you reach here and there and there. Then you keep looking at which states are you reaching with these numbers or with these words. And then since the automaton only has a finite number of states, one of those states has to repeat, right? But this means that then in your DFA, or in your automaton if you want, the state you reach here for some ni is going to be the same state that you reach later for some nj. And what this means is that the run corresponding to this fragment is a loop, and therefore you are accepting actually a word with infinitely many b's as a DBA. Okay? Everybody happy with this? Right? Good. So thank you, Bernd.
Welcome.
Yes, tomorrow Bernd is going to tell you absolutely everything about. Anyway, so how do we repair this? Well, probably all of you know how to, or many of you know how to repair this by going to a different model, a more powerful model, Rabin automata. So Michael Rabin is the general chair of this school, right? You have a few pictures of him through his life. And what is a Rabin automaton? So it's just like a Bush automaton. The structure is always the same. We only change the acceptance condition. And the idea essentially is, remember, a Bushy condition was just, we were representing this as a Boolean combination of G's, right? And G's are conditions of the form visit this set of states infinitely often. So in fact, for a Rabin condition, he didn't formulate it that way, but if you generalize it a little bit, what you have is just a Boolean, a positive Boolean combination. Positive is important, a positive Boolean combination of what? Of conditions of this form, Fg, where the idea is that now we are saying visit this set infinitely often and visit this set finitely often. Okay, so we just replace the atomic thing that we can say. Instead of being visit this set infinitely often, now it is visit this set infinitely often and visit this other set finitely often. Okay, and then take a positive Boolean combination of that. And Rabin, the original Rabin condition is a little bit more restrictive. It is actually a disjunction of things of this shape, but don't worry too much about that. So it's this generalized Rabin condition. And of course, every Bush automaton is a Rabin automaton, because you can always say, well, and visit the empty set only finitely often. That's always going to be the case. Okay? Good. And then the important thing is that, or an important thing for us, is that both an array, non-deterministic Rabin automata and deterministic Rabin automata, they are both closed under union and intersection. And for that, you just have to play a little bit, essentially, with the acceptance condition. It is just essentially a little exercise, a little bit more complicated than doing it for finite automata, but it's essentially the same construction. Okay? Good. So now, how do we get a DRA for, yeah?
I just wanted to say that parity conditions are, of course, also Rabin conditions.
Yeah. Okay. He's going to tell you everything about how to translate deterministic Rabin automata into parity automata tomorrow. More questions? Yeah. Which model? Yes, they are close under complementation. Yeah. Okay, but we are not. It's not obvious. It's not obvious at all. It's not obvious at all, but they are. Actually, I'm not going to show it. Okay. In fact, one of the good things of having to deal with LTL is that as long as you restrict yourself to LTL, complementation is for free, right? So whenever you want an automaton for the negation of your automaton, if your automaton corresponds to a formula, just negate the formula and construct the automaton. Good. Okay. So how do we construct a DRA for Fg, G formula, and then Fg phi, and phi is a GRW formula? Well, G phi then is also a GRW formula, and then you just go back there. It's just the same construction that we had before. You add just a loop going from the false state to here, and what you declare is that the accepting pair is now this one, right? You say that you want to visit the state false finitely often, and this means that from some moment on you will not visit the state false anymore, and therefore you are going to stay in the range of states that are accepted, right? So you are going to accept the formula, okay? So if we moved actually to this model, then the constructions are completely dual. In both cases, you just have to add one arc, right? In the one case from true to the initial state, in the other case from false to the initial state. Okay, everybody happy? Good. So then, of course, what Moshe now is thinking is, when is this going to stop, right? This is a never-ending story, no? I mean, you are going to tell me how to do it for until FG or until GF. In fact, what Moshe is probably thinking right at this point, or Orna there at the back, is, well, you are just dealing with the easy cases, right? And then at some point you will have to start with the real stuff. And, well, that's my claim. My claim is actually we are done. My claim is, in order to construct a DRA or an MBA or a limit deterministic automaton for an arbitrary formula, you only need, with respect to constructions on automata, what we have seen so far. You have to be able to compute automata for intersection or for union. You have to be able to construct automata for these fragments, and that's it. There is nothing else.
Now when you say Rabin, do you mean Rabin or generalized Rabin?
When I say, I mean Rabin, but yeah, you may have to degeneralize at some point. Okay, so it's just a matter of assembling the parts. But what we need is a theorem allowing us to see, which is going to tell us how to assemble the parts, right? But the claim is you only need this. Good. So that's the end, actually, of a set of slides, and I have to go to the next one. Okay, so we need to talk about what does it mean that the formula stabilizes with respect to a word, right? And for that, you just fix a word W, you fix a formula phi, psi, and then you know there are only three possibilities. Either psi holds for finitely many suffixes of the formula, almost nowhere, so from some point on it does not hold anymore. Or it holds for all but finitely many suffixes of the formula, so almost everywhere, right? Or it alternates, right? So if you picture, for instance, this formula, right? The formula A or C, right? Then it holds here, it holds there, it holds now in these points, and imagine that it continues holding. So the idea is that in this case, the formula stabilizes to true. Okay, and the stabilization point, so in cases 1 and 2, you are going to have a stability point, right? The point at which the formula has stabilized is going to be there. I'm sorry, I think again, I was changing the slides just before the talk, and that's not a very good idea. I should think about A or C, right? And this is the point at which A or C stabilizes. Okay, good. Okay, so now, imagine, I want you to picture the word that we are trying to, for which we are trying to prove a property or to see whether the formula, a property holds. I want you to picture it as a very long path, right? Imagine that the word is written on the ground, and it's a very long road. It starts in Egypt, and it leads to some nebulous promised land, but actually we have been walking for 20 years, and this has... No, for 20 years. We're in the middle, right? And we don't know how long this is going to take. And actually, well, for us, the word might well be infinite, right? So let's consider it's an infinite word. We have started to read it, the first 20 years of the word, right? So far we have read this prefix. And we keep updating the formula that we still have to prove, right? So we are being computing step by step this formula. So we know this formula. And recall, right, the word is going to satisfy the formula if and only if the remaining suffix satisfies this formula. Well, the formula is very complicated. It doesn't fit in any of the fragments that we have seen so far. And actually, Moshe is leading us, right? And even he doesn't have a clue about how to check this formula, right? And then now something happens.
You know why they went 40 years in the desert? Because Moses didn't want to ask for directions.
Exactly, right. But actually, Moshe didn't want to ask for directions, but something happened, right? How many of you know the story of the burning bush? Who doesn't? Okay, okay. The Bible is still doing not so bad, right? I mean, it's still working. So the idea is that for those of you who do not know what happens when you see a burning bush, you could also rephrase it as an angel comes from above, or the skies are suddenly clear, right? The idea is that God wants to talk to us, right? And give Moses a bit of help. And now I cannot help Moshe, I'm sorry, but the other day it worked so well that I have a little prop here. Can you come to the stage again? Take your phones, guys. No, come here. You know.
Somebody should take a picture with me there.
No, it's not. Yes, you just grab the,
Stuff.
you put it here, right? You know, have it there. Okay, guys, take your pictures. It's already on Facebook? Great, yeah. I like technology, right? Good, but the idea is that God is going to help us, right? And actually pay attention, this is important. Which help are we going to get from God? So let this be the set of temporal subformulas of phi which belong to this fragment, right? So think of the subformulas of the form f something or an until or something, right? And God is going to tell us, actually, is going to have pity on us, and is going to tell us, look, I'm going to tell you which of those hold infinitely often in the word that you have, okay? This is this set, right? It's the set of formulas which hold infinitely often. That's why I've chosen this name, GF, right, for the word W. And not only that, actually, he's very kind, and then he tells us what happens with the other formulas of FUM. He tells us, well, the other ones, of course, they only hold finitely often. And actually, I'm going to reveal to you that after 20 years, they are not going now to hold anymore. All the moments at which they hold, you have them behind you. You have already passed them. Okay? Everybody happy with that? So actually, what we know, what God tells us is, for all formulas here, right, they are going to hold infinitely often in the future, right? And for all the others, they are never going to hold anymore. Okay, so now the question is, we have to check a complicated formula, this AFW, phi W0I. And now we have got this help from God. Sorry? No, there are, you take these formulas. Some of them are going to hold infinitely often, right? So God tells us, here are they. And the others only hold finitely often, right? And actually God tells us, you have reached a point in your road at which you are beyond the stabilization point for all those formulas. Sorry? You mean that God cannot tell us such a thing? I mean, God, of course, can wait until we are there, until 20 years, and then he tells us, well, actually, I'm getting kind, right? No, of course, God cannot tell you that cannot pick any moment, or we cannot tell God, please, God, tell me now whether no, I mean, the idea is God waits until you are beyond the stabilization point and tells you, now you are beyond the stabilization point. Okay? So now the question is, how can we profit from this information? Okay, how can we use this help to replace this complicated formula, which is the one that we have to check, but a simpler one? And actually, that's not difficult, right? So we are going to, yeah.
Is equivalent to basically starting with automaton with 1 point, making deterministic choice, and then eliminating that 1 point?
Maybe, I don't know. The problem with Moshe is that whatever you say, he will always rephrase it as a question on automata, right? I mean, I mean, you are talking about theoretical physics, black holes, and heterogeneous, but isn't this an automaton which looks at the black hole? And so actually, I don't know. I guess it might be. Anyway, for this moment, just think logic, right? Just think about logic. We are doing logic. So interpret this formula. You know, it's a little bit difficult to find a right symbol for this. Interpret or let's call this as psi with advice x, right? And which means the advice x. That means, well, you know that all formulas in x are going to hold infinitely often. And you know that all the others in this FUM fragment, they will never hold anymore, right? So then let's try to transform psi into this simpler formula, right, by making use of this information. Okay, and then the cases in which we are actually going to transform the formula and do something interesting are the cases in which psi is of this form, right? And it's very easy. Imagine that psi is A. Right? And now God tells me, you know, A is in X. A is going to hold infinitely often. Well, unfortunately, I want to know whether A holds now, right? Whether it holds infinitely often in the future or not, that doesn't help me, right? So actually, A remains A. But now imagine that A, right, God tells me, actually, no, A is not in this set. This means A is never going to hold anymore. So then I can replace A by false. Okay, because it's never going to hold anymore. It is just, I may as well replace it by false. Imagine that you have a formula of the form f psi 1, and God tells you, well, actually, psi 1 is going to hold infinitely often in the future. Then you might as well replace f psi 1 by true. Okay? And if God tells you, well, actually, it's never going to hold in the future, right? Then you replace psi 1 by false. What about an until? Well, if God tells you that psi 2 is going to hold infinitely often in the future, then actually you can replace the until by a weak until, right? Because you don't need the information anymore that psi 2 is going to hold. You don't need to check that because God has already given you the information. By the way, you were asking why do we need the weak until? There we need the weak until, okay? In order to be able to syntactically express that we now have this information. Okay, and if God tells you psi 2 is never going to hold anymore, you might as well replace this by false. Okay? Sorry?
I could also replace it with always psi 1 or psi 2.
Always, you mean where here?
Yes.
Yeah, always psi 1 or psi 2. No, why?
Because it will give you psi 1 until psi 2.
No, but it is exactly the same. It is the weakest formula that we need to check in order to... It is stronger than you need, right? No? Well, let's take it offline. I'm very bad at doing these things in front of a screen. Anyway, so, and then the M, you know, this operator that we don't even know what it means, but it's some kind of dual, so it doesn't really matter. And what happens with then you have the other formulas, the formulas of the form next something or G something. Well, then you just, you know, then you just let them, you propagate the operation, let's say, of taking the advice inside, right? Or you also make it distribute over OR and AND, okay? So the result of obtaining the advice for psi 1 and psi 2 is the result of applying the advice to psi 1 and result of applying the advice to psi 2. Okay? Good. So the interesting thing for us is, well, actually immediately from this syntactic transformation, what you obtain is that whatever psi is, after the advice, psi, the new formula, psi with advice x, is a GWR formula. So it belongs to the fragments that we know how to check. Okay, so the idea is that we can really make use of God's advice because now we only have to check a GWR formula, and we know how to do that. Good. So this is the theorem that you can formulate. Take phi, let phi be a formula, W be a word, X be a set of FUM formulas of subformulas of phi, right? And now imagine that X is the set, the right set. X is the set of subformulas that hold infinitely often. And imagine further that, you take a suffix, wi, and that suffix is beyond the stabilization point. So all other formulas, right, they are not going to hold anymore. Well, then actually what you know is that the suffix I is going to satisfy this formula, and remember that's equivalent to the word W satisfying the original formula, right? If and only if the suffix I satisfies this formula. So actually this is the way of profiting from God's advice. This is the weakest formula that has to hold after we have been given God's advice. Okay? Good, so this is the interpretation, right? With his help we can replace this by the GWR formula. Everybody happy with that? Good. So this is going to be an example. So imagine we have this formula, which is one of the simplest formulas that doesn't fit in the cases we have. Then we could have a word like this, right? A, B, here A holds, only A, only B, here none of the two, A, and so on, with a B omega tail. And imagine that we take the point, we have the point I is equal to 8. It is beyond the stabilization point. So because we have, this is the prefix we have, and actually if you compute the formula that has to go at that point, it is still this one, right? And now God comes and tells us, but actually, B is going to hold infinitely often, and the others do not hold infinitely often, which is the formula that you still have to satisfy actually true. Okay, so God's advice at this moment is enough to, you don't have to do anything else. Okay? Good. So, right, let me just go to here. So now let's imagine that the story goes a bit differently, right? So actually God tells Moshe, want to talk to you. But now when Moshe comes back, we ask him, well, what did you get? What advice did you get? And he says, well, he wasn't very happy for some reason, wasn't in a very good mood. He kept talking about the golden calf. Yeah, have you heard anything about the golden calf? And then actually what he told me is that, some formulas are going to hold infinitely often. Did he tell you that these are all the formulas that are going to hold infinitely often? No, he didn't say anything about that. He just told me these ones hold infinitely often. Did he tell you something about the stabilization point that the others are not going to hold anymore? No, he didn't say anything. All I got is that these formulas are going to hold infinitely often. I don't know anything else. Okay. Well, can we still use the formula we had? We just computed a moment ago. Right? Well, the idea is, yes, we still can get something out of it. The theorem that we get is this one, right? That, this formula we computed, if that formula holds, right, then this formula will hold, right? So if we manage to check this formula, this will be good enough for this one, for wi to satisfy this, and therefore for this. But we don't get the other direction, okay? It is not the weakest formula anymore, but it is some formula that will be able to give us the desired result, right? Intuitively, why is that? Because when we take this replacement, the replacement that we are doing here, for instance, remember that then, so what do we do with a formula of the form f psi? If God has told us it is going to hold infinitely often, we replace it by true. And otherwise, before when we had full advice, we were replacing it by false. Now we still replace it by false, and that's conservative, right? Okay, because God hasn't told us anything about this formula. It may or may not hold infinitely often, but we just we assume that it's never going to hold. We replace it by false. And why is that conservative? Because we are working in negation normal form. And in negation normal form, assuming that the formula does not hold is always a conservative option, right? If we still manage to prove that the whole formula holds with that assumption, then actually we have proof that the formula holds. Because the only thing that can happen is that subformula is true, and if that subformula is true, things are better for us. Okay? So this is what we get. Okay? And something that we also get is actually that this point wi, right, we can choose it arbitrarily far away, right? Because actually, essentially the idea is that, if wi satisfies this, then that implies that if we go farther, that still satisfies that. Okay, and this has to do with the fact that, you know, the important thing for this I is whether it's a stabilization point or not, but once you have the stabilization point, it doesn't matter how far you go, right? You can go arbitrarily far. Okay, so the interpretation is that even with less help, if we are able to check this, then we are done. And we can also choose the I here arbitrarily large. We can wait as long as we want in order to do this. Okay, so, and here you have another example. So let's see, imagine we take the same formula, we have a different word, and now, you know, God has told, could have interrupted us at any moment, not necessarily a stabilization point at I equals 1, for example, right? And then we have that the prefix W01 is just A, and you can compute which is the formula that remains to be satisfied. It is this one. And now God tells you A holds infinitely often, but that's all I am going to tell you. That's all the information you have. Well, if you compute this formula, right, what you obtain is GA, and indeed GA is enough to prove that the formula holds, right? But it is more, maybe it's more than you have to prove, but it is okay. Okay? Good, so that's all you have to keep in mind. Good. So, and then Moshe says, oh, but I have it. Actually, you know, we should not be bothering God with this stuff. We should keep him for the important things, right? Splitting seas, stopping the sun, and things like that. You know, this is just a temporal formula, right? Come on. We should be able to do this ourselves. Okay? And then the idea, so Moshe thinks, well, this is the theorem that we have now, right? If we are able to, if the suffix satisfies this formula, then, you know, actually the word is going to satisfy the original formula. And then the idea is, well, actually you can reformulate it like this. The word satisfies a formula if and only if there exists an advice, right, and an I, such that, you know, the suffix satisfies this formula, and this is just telling us, you know, we check actually ourselves without resorting to God, we check that actually God's advice is good, right? So we guess the X, and we check that the X is good. And in fact, you know, there are only a finite set of possibilities for the X. So actually, there are many peoples of Israel, there are at least 12, right? And they have many people, so they can take care of, yes, Moshe goes to Levi and Judah and whatever and says, you are in charge of this X, you are in charge of this X, you are in charge of this X, right? Good, so actually this 2 is just checking that indeed the X is good advice. And why is this theorem holding? Well, why is there such an X? Because you take the right X, right? You take the right X, the X which really is the set of all formulas which hold infinitely often, right? And why does the other direction hold? Well, because of this theorem, because you can never do anything wrong, right? If you pick any X, and then it turns out that this holds, then you know that by taking this formula, you can satisfy the original formula. It's good enough. Maybe it's not, you know, maybe you are not doing it optimally, maybe it's not the weakest one, but it's good enough. Okay? Good. So then Moshe is very excited, right? And he's saying, well, I think we can do it ourselves, right? But of course, then the peoples of Israel, they are always very skeptical about their leaders, right? With good reason, like in any other country. And then they say, okay, well, yes, but how are we going to check 1 and 2? You know, okay, we can do it for all the possible X's, and then we have to check 1 and 2, but how are we going to do it? And Moshe says, well, come on, but this is a GWR formula, right? It is actually easy to do that. And then Moshe says, and look, imagine that this psi is a FUM formula. Then this is a GF-FUM formula. So we also know how to do that. But then the peoples of Israel said, and if it is not a FUM formula, what? And then Moshe retires and starts to think, and thinks, and thinks, and thinks, and then goes out to the desert and asks for help, right? Says, what about that? I don't have a clue, right? Could we get a bit of help? right? And then God shows mercy again and says, well, okay, I appreciate the effort. You haven't done your homework completely, but okay, you're not doing that bad. Let me help you a little bit, right? And then the idea is that, well, there is no reason why we shouldn't get dual help from God. God was helping us with which formulas hold infinitely often, right? So now what God can tell us is which formulas hold almost everywhere, okay? So God tells you which formulas hold everywhere, okay? And so he reveals to us that he chooses a point beyond the stabilization point, and then what he's telling us is, well, you know, actually, these are the formulas which hold almost everywhere, and actually you are beyond the stabilization point, so actually from this moment on, they are going to hold forever, okay? And what about the others? Well, for the others, you know that not Fg psi holds, okay? This is all completely dual. So now you can do exactly the same thing. You can try to exploit this information, right? This is now the Fg substitution, if you want, or operation instead of the Fg. And now, for example, take this one, right? Imagine that your formula is of the form G psi 1, and God tells us psi 1 is actually in the set, so then we can replace this by true, right? And we can replace otherwise the formula by false. And, you know, the same thing goes through, okay? So actually it is completely dual. And again, you have the lemma that this is now, you have got rid of everything which was, of all the G's, of all the W's, of all the R's. So this is only an FUM formula, right? Good. So now then, what does it mean to get dual help from God? It means to get a set Y, okay, which is in the set of formulas that hold from some point onwards, right? So this is the theorem we had. And, you know, the problem is that we don't know how to check this, right? So now we get help from God. And God tells us, you know, okay, I'm going to give you, this is the second kind of advice from God. God tells us that some formulas, some GWR formulas are going to hold almost everywhere, and that you are actually, and it doesn't tell you anymore that you are beyond the stabilization point, right? It's the weak advice from God. All we know on top of that is that this is holding, these formulas satisfy, hold from, are going to eventually hold forever. Okay? Well, so then, actually, you know, if we go back, this is what we had to check ourselves, and we didn't know how to do. Now, this is what we have to check ourselves with God's help. Okay? And the problem is, of course, that if now we would like to do this ourselves, well, the problem is that we would have to check all the x's and all the y's, right? And the problem is that we still have to check this. And it seems as if we are stuck again, right? It seems as if now, okay, well, and then what happens if this is a FUM, and what happens if this is a WR? But again, we are going to need to need help from God, and then this is going to have no end, right? But now this is the moment at which Moshe is going to have this idea. But now, you know, now we need help only about the smaller formulas. We only need help about formulas of this fragment, GWR of FUM of phi. And therefore, that means that when you continue this process, the process is going to finish, because you start with a process where you need help about formulas, subformulas, temporal subformulas of phi. Then God helps you. Then you find out, okay, if I do this, I can profit from this help from God. And then then you see that you still need some help from God. But the idea is that you have done some work, and then you observe that you only now need help from God for smaller formulas. So you can iterate the process, right? And this process has to terminate. And it ends with what? With either a GWR or a FUM formula, okay? Or a formula of the form FG, FUM, or GWR, or whatever, right? So this process terminates, and then you don't need God anymore, Well, so we can do it ourselves and keep him for the important things.
Still in the I, right?
Wait a second, yeah. So the idea now is that you could think, well, but this is going, maybe yes, nice, but the theorem, how are you going to formulate it? It is going to take forever, right? You're going to keep adding things until you are done. Well, no, actually, this is the formulation. And let's say that the full purpose of this course is just to bring you to the point where you understand this. Right? This is the master theorem. What is it saying? It is saying, take a formula, take a word. A formula, the word satisfies the formula if and only if there exists a set of cause-safety subformulas and a set of safety subformulas, in case you know what cause-safety and safety is, and an index I, right? Such that what? You can check that the x's hold infinitely often with using the advice of y. You can check that the y's hold from some point onwards using the advice from x. And there is no circularity here, because actually you are always going below in the order or in the subformula order, right? And moreover, you can check that wi satisfies, the formula that you have to check in order to check phi, but after using the advice x. Okay? So this is what we like to call the master theorem. And notice that this is a GWR, this is a GWR formula. Okay? This is a GFFUM formula. We also know how to do that. This is an FG GWR formula. We also know how to do that. Okay? Well, we have to guess the x, we have to guess the y, we have to guess the I, right? But the idea is that there are finitely many possibilities here, so then we can just consider all the possibilities, right? And the idea is that if you want, you could assume that you have an automaton dedicated to each possible choice of x and y, right? You have one automaton for that. So you reduce the problem, if you want, to constructing automata for each choice of x and y, which check these three properties. So you have to construct an automaton that checks this and that, right? But now the advantage you have, what you have got, is that now you know that these three formulas, they are easy formulas, right? They are not complicated formulas. Good. So let me just, let's try to go through an example.
Still have to deal with the I, right?
Okay, let's come to let me start with, let's go slowly, because this takes a moment. Okay, so let's consider an example. Imagine that our formula is G, A until B, right? And now we choose the mode, if you want, in which, okay, let's choose for x is equal to B and y equals to the empty set, right? So the idea is that we know that B holds infinitely often, and then we don't know anything about y, right? So which is the condition that you have to check? Then you have to check that this is indeed true, so you have to check that W satisfies GFB. You have nothing to check here, right? Now what you have to check here, well, it depends on the I, right? Because for the I, the formula is transforming with the I. You are going through the formula, and the formula is changing. For example, for I equals to 0, what you have to check is G, A, weak until B. Okay? So these formulas, we know how to do this, right? And this is what you would have to check for I equals 0. Let me show you another example. We have gone through that. Let's take now a tricky formula, right? It's G, A, or F, B, and G, C, or F, D, right? And I've chosen this one because now we can see different possibilities, right? What happens if we take x equals D and y equals the empty set, right? This means now we know that this is going to hold infinitely often, or at least, I mean, we are assuming that this is going to hold infinitely often, and that's why we have to check this, right? here we only have to check true. And then in this case, what happens is that knowing that the D holds infinitely often, you know, it means that this C or this is going to become just C. Sorry, this is going. We are going to be able to replace this by true, and true or C is going to be true. So this is going to become true, and then all we have in the end is G, A, or F, B. Okay. So the idea is, if you one possibility of making this formula true is to check, or one possibility of proving that this formula is true for a word is to prove that the word satisfies GFD, and then prove that the word satisfies this, right? Another possibility is, you know, that you get A and empty set. Well, this means that now you have to check GFA, and actually this is not going to help you very much, because, you know, you have to check that the formula you have to check is this. So actually, in this case, what you are going to do is replace, let me see, you are going to replace the FD by false, right? You are going to replace, Salomon, help me out here. Where are you? Sorry, this one, right? We can replace this one by false, right? We are going to, when we do the substitution, we are going to replace this by false, and what we are going to retain is GA. So the idea is that, well, we are done if we prove GFA and GA. You know, of course, this one implies that one, right? But, you know, this is what you get in this case with this choice of X and Y. And what do you get in the choice, in the case in which, you know, X is the empty set, Y is the set B and C? So in this case, what you have to check is FGB and FGC, right? This is your, and the idea is then, okay, and how can you use this information in order to prove the formula? Well, if you know FGB and if you know FGC, actually in this case, actually you have already proved the formula. And if you want, what the theorem is telling you is there are finitely many of these things, right? And for every word, one is going to hold. Okay? So therefore, when you check them all, then you are getting, if you have automata for all these cases.
For I equals 0 only?
Yeah, okay, let's see. Now the idea is, what is this I? What is this condition 1, right? What this is telling you is that, well, WI, the condition is telling you WI satisfies this formula, right? But this formula is changing with the I, right? So actually, for I equals 0, this is what you get. For I equals 1, you will get something else. For I equals 2, you will get something else. Okay? Good? Everybody happy? So I think then, I have just 5 minutes. I think this is a relatively good moment to stop, because, you know, then what are we going to do tomorrow? The idea is that now the problem of computing NBAs of exponential size for arbitrary formulas can be solved using this, and only using the constructions that we did, that we have seen at the beginning of this lecture. The problem of constructing deterministic Rabin automata for arbitrary LT formulas can be solved using this, and just applying the constructions that we have seen for the deterministic case, right? The problem of constructing limit deterministic automata for arbitrary LTL formulas can be solved doing this, okay? Actually, the idea is that if you have come up to this point, then instead of the 4 or 5 papers that you would have to read in order to construct all those automata, you have to learn about the Safra construction for doing determinization. You will have to learn a couple of, well, you have to learn the paper about constructing NBAs. You will have to read the paper showing you how to do, how to go from NBAs to limit deterministic NBAs. And instead of all that, it's going to be 1, 2, 3, 4 slides, okay? Which I don't show you because you should not read them at this point, right? So tomorrow essentially will be about 4 slides. Since I have done a bit of progress, I probably will add a couple more, right? And the other part of tomorrow will be the following. Well, all this is implemented. It's not published, but it's implemented. How can be that? Usually we publish and then some years later we implement. Well, actually, the master theorem, let me show it in all its glory, right? The master theorem is the end of a long process. So a process that actually Jan Kretitsky started in 2012. And, we have been having versions of this, which we have implemented, right? But they were never quite as nice. Actually, the previous version, for example, didn't have this, and then it was a bit more complicated. Now we have this very nice version where the idea is just that you use the y's to check the x, you use the x to check the y's. And that is not a circular argument, right? Well, this means that actually we had implemented all the previous versions, and for all the previous versions, we had already the software, so actually implementing the new version once you have the theorem, or once it's just a matter of a couple of days. So Salomon then will show you tomorrow a demo of the tools that we have. The first, there are something like 2 versions of the tool. The first one is called Rabinizer, right? So I'm very happy that I am in a school with Michael Rabin as general chair. So did you tell him that there is the Rabinizer tool?
No, I'm going to.
You're going to, yeah. Because I think he can enjoy that, right? And the other one is is OWL, which stands, so the OWL, OWL, which stands for Omega Word Automata Library. Okay, good. So this is then the plan for tomorrow. But now the plan for today is that now you look at this for 1 minute and a half, right? And you appreciate its beauty.
So here you reduce it. There is x and there is y. So number of such possibilities is exponential.
Yes.
So you have exponential many Rabin conditions.
Exponentially many Rabin conditions. No, what you have is exponentially many Rabin automata.
Yes.
Yes.
And x corresponds to automata or to from this theorem, what you deduce? Is that
Okay, so the idea is that
He has not deduced
no,
yet.
Yeah.
what you're going to prove
no, what I am going to show you is how to construct the deterministic Rabin automaton
for phi.
for phi.
And what will be the size of this automata?
It will be double exponential.
Double. Oh.
Well, I mean, this is a deterministic Rabin automaton, right? You cannot do better. It's going to be the union of an exponential number of Rabin automata, one for each choice of x and y.
Yeah. And the number of Rabin condition also will be exponential or double exponential or triple exponential.
No, not triple exponential.
But
Exponential, yeah. So
so for every pair x, y, you will have a Rabin condition, yes?
yes. Well, I will have a Rabin automaton,
Okay.
and then you take the union, right? But you know how to take the union of deterministic Rabin automata. Okay. Good. So that's it. Thank you.